Hi everybody, I'm going to go over enolate retrosynthesis and the irreversible steps that each reaction has. So we're just going to kind of summarize the enolate reactions that we've covered so far and think about, what kind of retron are we looking for? So what functional group are we trying to identify? What reaction does that go with? What starting materials does it break down into? And what irreversible step makes it actually possible? Okay, so we're just going to start with where we began. So we're going to start with alkylation. So for an alkylation reaction, we're just using an enolate and then adding it to an alkyl halide or an epoxide or something like that. So really we're looking for a single carbonyl. And the alkylation is one of the harder ones to identify, I would say, just because you're looking at a bond that it's a little hard to tell that there was a bond formed there initially. Okay, so we're looking for some kind of retron like this. Your X can be an aldehyde. So you can have an aldehyde, you can have a ketone, you can have an ester. You've got options there in terms of what carbonyl you're actually starting with. But the point of the matter is that you're forming that bond, okay? So I might actually highlight that too. Okay, so we're making that bond right there, which is essentially the alpha beta bond. So if we break that apart into the starting materials for an alkylation process, we're looking at some type of enolate plus some alkyl halide. Okay, and I'm just going to put Lg there, and their Lg can equal chlorine, bromine, iodine, or the tosylate. Okay, you can also do epoxides. Okay, so epoxides will also work here. So for the alkylation, the irreversible step is the formation of that carbon-carbon bond. So you can't really go back from here because you'd have to break that way and then put a positive charge on there. So the actual carbon-carbon bond formation is the irreversible step. Okay, so we can't go back to the alkyl halide or the epoxide. Okay, it would be very, very difficult to do that. So this is very similar to kind of like the Grignard reactions, where once you add that, you form that carbon-carbon bond, you're done. You can't really go backwards. Okay, so that's our alkylation. Cover that. Okay, so the alkylation. The next one that we talked about was the aldol reaction. Okay, and we really talked about two different ways that you could do the aldol reaction depending on what base you actually used. Just gonna scoot this up a touch. So we talked about if we used LDA, then we could end up getting to the beta hydroxy ketone. Okay, so again, our starting material, our starting carbonyl that we've made the enolate from could be an aldehyde, it could be a ketone, could be an ester, really anything that would allow us to actually make the that enolate. That's really all we're looking for here. Okay, so this is going to be our beta hydroxy carbonyl. Okay, we also called this the aldol addition product. And really the only way that we can make this form as our final product and not as a step in the product, a step to make the product, is you have to use LDA to get this. Okay, so if we want to stop here, we have to use LDA as our base in order to isolate that aldol addition product. Okay, so if we break this down into its starting materials, again, we're looking at forming this bond right here. Okay, so in the retrosynthesis, that's the bond that we're activating. Again, we've got the alpha and the beta position, so we're making that alpha beta bond. So if I go backwards there, I'm going to start with my enolate, and I'm going to get to this carbonyl, okay, as my electrophile. So this could be a ketone or an aldehyde. Right, so ketone or aldehyde here for the aldol. And as we'll see as we go along, pretty much we're using the same nucleophile each time. It's always going to be an enolate. The thing that's going to change is your electrophile. So the different electrophiles are what gives us these different types of reactions here. Okay, so we get a ketone or an aldehyde out of that. We have to use LDA, and the irreversible step is actually the first deprotonation. Using the LDA to form the enolate. Okay, so the formation of that enolate is our irreversible step here. So everything after that is actually pretty much irreversible as well, because we can't ever go back to our original starting materials. Okay, meaning the carbonyl before it's hit the enolate. Okay, so then we've got the we're not at Claisen yet. So then we have the conjugated carbonyls as our products, which counts as another aldol reaction, because again, we're using the same electrophiles. This is just a difference in base. Okay, so if we want to make the conjugated carbonyl, so conjugated aldehyde, you could do a conjugated ester, conjugated ketone, any of those. Okay, so this could be an enone, enal, etc. Okay, because our X again can be H, it can be R, so any carbon groups, could be an ester. It's a little less common, but you can do that. So if you want to get straight to this conjugated carbonyl, you can use any of the oxygen bases, so OH minus or OR minus. If you do want to use LDA and get this in the end, you have to do an additional like an acid quench and some heat to help that happen. Okay, so that's going to be our conjugated carbonyl. So in this one, we're actually doing a very similar process where we're actually going to be going from this to that. So the beta hydroxy ketone is essentially the last kind of step backwards, or the first step backwards when you're thinking retrosynthetically. So essentially what we can see here is we can go backwards really quick. And this is how I would recommend doing these ones, because they're a little bit trickier, because you can't quite see where everything came from necessarily. So I would step backwards before you do the elimination process and say, okay, I probably came from this beta hydroxycarbonyl to get my alkene in place. So once you have the oxygen there, it's a little bit easier to see that you're making that bond. Again, it's going to be the same alpha beta bond, and we can kind of think about that over here, right? we can kind of transfer those. We're still making the alpha beta bond, where the beta is going to be your electrophile, the alpha is going to be your nucleophile, and you're going to get those two things together. So when we break this down, again, we've got the same nucleophile, got our enolate, and we've got our electrophile, which in this case is going to be the same as the ones up above, where this is just a ketone or aldehyde. Okay, so for the, actually I might as well just not make this all cramped because I have plenty of space. Okay, so for the irreversible step, that's actually going to be the formation of the final conjugated system. So your conjugated carbonyl, whatever that is, the formation of that is going to be the irreversible step. Okay, so you're forming the thermodynamic product. Just not doing myself any favors here by not using the full width. Okay, so this whole process is reversible until you form that very last final product. So that's why when we're doing LDA, we can stop there, because once we have all of this stuff, we already have an irreversible step in the very first step. And then we can just keep that, because you're going to end up making an O-, which you're going to end up having to add some water to get it protonated. And it's just like a Grignard, where you kind of have to do that workup step. But this is going to just pop out that completely finished conjugated enone or enal or whatever you're working with. And that's the only way that you're going to be able to build up product, is if you are forming that conjugated system. Okay, so because it's nice and conjugated, it's really low energy, and that's why it's favorable, and that's why it's kind of the final irreversible step. Okay, so now we're on to the Claisen. Just line there. Okay, so the Claisen reaction, that's going to be using some sort of ester electrophile. So we're kind of moving along from ketones and aldehyde electrophiles to ester electrophiles now. So the retron that we're looking at there is going to be a 1,3-dicarbonyl. Okay, so we're looking at 1, 2, 3. So the thing to keep in mind here, so our X1, again, it can be HROR. X2 can be the same. Okay, we'll have some specific rules for what the starting materials need to look like, but this is our 1,3-dicarbonyl, and that's really what we're looking for. So again, we can do the same situation here, where we can say alpha and beta, and we're making that same alpha beta bond. Okay, so again, we're still making the same alpha beta position bond. So when we break that down retrosynthetically, we can get to 1 enolate, right? So same nucleophile in all cases here. And then we have to have some sort of ester starting material, okay? So in this case, oops, sorry, we have to have a leaving group potential in order to form that final carbonyl. So this has to be an ester, and that's the total difference between the claisen and the aldol. Otherwise, they're very similar. Okay, so the other thing that we need to keep in mind here is with our irreversible step, we have to deprotonate. And this is a must have a proton between the two, or between the 1,3 dicarbonyl. Okay, so an example of that would be, we have to have one H there at least, okay? Because the deprotonation of this is our irreversible step. Okay, and the whole point of that is that this position, this H, is very acidic. So it's a very much a one-way trip between like an O- or something base. You go grab that H, that pKa difference is such that the enolate form of this is favored, and because it's not very basic anymore, not like a regular enolate, it's not going to do anything else. So it's not quite as good of a nucleophile. So it's just going to chill out there, and that's going to be our irreversible step. Okay, so our final reaction is the Michael reaction. I'm gonna just kind of try not to move that too much. I don't like how it. Okay, I'll try to even those out later. So the last reaction is one that we covered yesterday, and that's the Michael reaction. So the retron that we're looking at for this one is a 1,5 dicarbonyl. So this is probably one of the hardest ones to see because it's just so far away. So the evidence of it is kind of spread through a starting material possibly, which makes it a lot harder. So again, X1, we can have that be an aldehyde, a ketone, an ester. Same thing for X2, aldehyde, ketone, or ester. And we've got this as our 1,5 dicarbonyl. Okay, so if we look at this, let's go ahead and number things out a little bit. So we've got the alpha, the beta, and technically we've got alpha, beta, right? So this is the beta position for both of them. You can split this in any way. I'm going to keep it the same. So I'm just going to look at this side. But again, we're still looking at the alpha beta position according to one carbonyl as the bond that we are going to be forming. So we're still forming that alpha beta bond, and we can break that down to one enolate. So again, same nucleophile here. And in this case, we need to have this beta position according to this carbonyl be an electrophile. So the best way to do that is to just go ahead and make that into an alkene. And then we're going to end up doing that conjugate addition into our 4 position over here. Okay, and that looks really wonky, so I'm going to fix that. All right, so we're going to end up adding to this carbon and then getting to that final 1,5 dicarbonyl. It's a tricky one, this guy. So I'm just going to go ahead and number this out so that you can see how we count the 1,5. We're numbering from the carbonyl to the carbonyl. Okay, so 1, 5. All right, so for this one, keep in mind here that often the enolate in this situation is going to be one of those 1,3-dicarbonyl enolates. So that's probably the most common one in terms of doing this Michael reaction, just because at that point, your irreversible step is the deprotonation of this. So you have a lot less issues in terms of overlapping enolates with similar acidities and stuff. As soon as you throw in a 1,3-dicarbonyl, your base is going to go straight for those acidic protons and not any other carbonyl protons. So depending on if X2 over here, if that's a ketone, for instance, and you throw in a 1,3-dicarbonyl, that is for sure going to be your enolate, and you won't have any weird aldol reactions happening and messing things up if you want to do the conjugate addition. Okay, so our irreversible step here is going to be the initial deprotonation in the case of a 1,3-dicarbonyl enolate. Okay, and if not, then it's a little bit more awkward because you have to tautomerize this. But generally, we're going to stick with this for our Michael addition. So we're just going to keep the initial deprotonation. I'm actually going to take away the parentheses here. So forming that enolate is going to be our irreversible step for the Michael reaction. So hopefully this kind of helped to summarize some of those reactions a little bit more, put it in a bit more of a perspective of, you know, how do we break these things down? What irreversible steps should we be thinking about? And getting going with some of those more challenging synthesis problems. So as always, let me know if you have any questions, and I will see you all later.